So conservative forces, we're dealing with energy being overall conserved here, right? Okay, so conservative forces are things that we are usually pretty focused on, okay? Forces for which the work does not depend on the path that's taken to get there, okay? Gravity, the elastic force of a spring, coils, those types of things exert conservative forces, okay? Those are going to be the ones that we are really concerned with, because our overall goal here is to see how energy is conserved. All right. However, of course, we cannot just have conservative forces. We have to have non-conservative forces as well. Okay, so for non-conservative forces, the work that is done does have a dependence on the path it was taken to get there. Okay, so friction, forces like friction, it depends on the path to get there, how the object moves, where it has to go. Air resistance, tension, all those things, the work is dependent upon the path that it takes. All right, so we're looking at two different types of forces here, conservative and non-conservative. Okay. When we looked at potential energy yesterday, what was our equation that we found for potential gravitational energy? MGY. Okay, our potential energy equation for gravitational potential energy is MGY. What type of a force would be gravity? What type of a force would gravity be? It's a conservative force, okay? We also calculated potential energy for springs, right? What was that equation? It had K in it, yeah? 1/2 kx squared. 1/2 kx squared. Okay, so when we calculate potential energy, we can only calculate potential energy for conservative forces. Okay, and we only have two equations for potential energy: gravitational potential energy and spring potential energy. Okay, so we can only calculate potential energy in those really two instances, gravity and with springs. Okay, if we're dealing with a vertical spring, it might have both forms of potential energy. But whatever, okay. So anyway, potential energy can only be found by things that are having conservative forces exerted on them. So this is a lot of equations. You only need to know the bottom one, but I'm going to walk you through how we get there, okay? You only need to know the bottom one. I'm going to show you how we get there, okay? And really the bottom one, not going to be one we use a lot with non-conservative forces, but I just want to show you our whole process so that you know where we came from when we end up. All right, so we know that our work net is going to equal the work of our conservative forces plus the work of our non-conservative forces, okay? Total work done has to be conservative plus non-conservative. We also know that the net work done is going to be equal to our delta kinetic energy. Okay, we learned that our first day in this chapter. Work is equal to delta kinetic energy. So if we substitute in our net work here for our delta KE, we get delta KE equals conservative plus non-conservative. Okay, are we on the same page so far? Okay, again, you don't have to know this path. I'm just trying to introduce it to you so that you kind of understand where we're coming from. All right, if we rearrange this equation and move non-conservative forces to isolate non-conservative forces by itself, we get the non-conservative forces equal delta kinetic energy minus conservative. We just talked about that conservative forces can only have potential energy, okay? Or potential energy can only be found by things that are having conservative forces exerted on them. So the work done by conservative forces is equal to negative delta potential energy. I'm sorry, okay? Potential energy. Why would it be negative? Any idea? Yeah, because it's going to be maybe a gravitational force, okay? Or our coil, our spring, okay? So when we plug these back in here, we're going to substitute our conservative force in for our negative delta potential. We're going to substitute our kinetic energy and our non-conservative force so that we see work done by non-conservative forces is going to be the sum of our kinetic and the sum of our potential energies. Okay, so non-conservative forces have both types of energy. It's going to be the sum of those two types of energies. All right, again, you don't have to have this path memorized. I'm just showing you how we get there. All right, work done by non-conservative forces acting on an object is equal to total energy change. Okay, that's what we just talked about. That's the equation you probably just wrote down. This is the same one that was in the box. I'm just rewriting it in word form. All right, a review of non-conservative forces, things like friction, tension, air resistance, or any applied forces. Those are the non-conservatives. Okay? All right. What if we have no non-conservative forces acting? What if we only have conservative forces? Things like gravity or a coil. Okay, so what do we do in that situation? Okay, we're going to take our equation here. If we have no non-conservative forces, this is all going to equal 0. Okay, do we see that? If we only have conservative forces acting, that means we're going to have no non-conservative forces. That means the work done by non-conservative forces will be 0. Okay? Are we clear so far? Okay. Again, we don't need to know this path to get there. I'm showing you how to get to our overall goal. All right? I want you to think this through conceptually more than having all these equations down. All right? I'll tell you the equations that you need to know and that you need to actually write down. I'm showing you how we're going to get to our final product. Okay. So if we know that there's no work done by non-conservative forces, we're going to start focusing on conservative forces, gravity, elastic coils or springs. Okay. The total energy now by these conservative forces is going to be called the mechanical energy. Okay. The total energy of a system is going to be called the mechanical energy, and it's the sum of kinetic and potential. This is one you will have to know. All three of these. All three of these. Okay? These are conservative. Conservative, because energy is conserved. Okay? Since we know that energy is conserved, this is our mechanical energy right here. It's our total energy of the entire system. Okay? That's going to be our kinetic energy plus our potential energy. Down here, the equation is showing the energy at two different points in a system. Okay, so let's say that your book likes to use roller coasters a lot as an example. Okay, so let's say we're on a roller coaster and our system starts here at its peak height at the top. Okay, if it starts from 0 velocity, if it's starting from rest at the top of the system, what would our kinetic energy be? If it has 0 speed, what would its kinetic energy have to be? 0. Okay? It has no energy. So that means all this energy at the top of the system must be potential. Okay? What if we get about a halfway point? What will the ratio of kinetic energy be to potential energy? Half. Yeah. Half will be kinetic energy, half will be potential energy. If we reach all the way to the bottom, okay, absolute bottoming out, what would our energy be in this position? All kinetic, no potential. It has no more potential to fall, okay? Because this is gravitational energy, it has no more potential to fall any lower in its path, okay? Yeah. Here's what the actual principle of mechanical energy says. You do need to have this into your notes, okay? So read it over, write it down, learn it. All right. So if we're looking to find the energy at any point along this path, we can find energy using this equation, okay? This energy equals kinetic plus potential. If we substitute the equations we know in for kinetic and potential energy, we learned last class that kinetic is 1/2 mv squared, potential equals mgy. We're just going to do a simple substitution to solve for that. Okay, if we want to find the total energy of a system, we would use this equation. Okay, so this is a big one. Okay, y is height above the ground, v is object speed at any point. Okay, I think we already know that. What type of potential energy is this right here? Gravitational or spring? Gravitational potential. Okay, it doesn't have the K, it doesn't have the spring constant in it, which means we're looking at gravitational potential energy. Okay? So this is the big equation. What about, this is for energy at one point in the system. What if we're trying to look at energy at 2 points in the system? Any ideas? Yeah, Cole, what do you think?
He's going to do mg delta y.
Mg delta y? Not quite. No.
Wait, so that first one is for one, that's for one.
This is for 1 point in the system. Okay, so this would be for energy at point 1. Okay, we learned that energy at point 1 is going to equal energy at point 2, right? Because energy is conserved. So that's what's going to take us to our next equation, which is a little bigger. All right, so since we know energy at 1 point, we can look at energy at 2 different points in the system. Since we know that energy at the second point is going to equal energy at the first, we can plug in our kinetic and potential, kinetic and potential. Like I said, I switched it so that I usually put the initial on the left, so that's the subscripts that are the ones, and I usually put the final position on the right. Okay, you can do it either way. It does not make a difference. You just have to be consistent as to what's the initial and what's the final. Okay, so this is our big equation that we have been working toward. All right, let's try this. It says if the height of a stone is 3 meters, calculate the stone's speed when it has fallen to 1 meter above the ground. Okay, so basically a stone is dropped. Okay, it starts up here at a height of 3 meters. It falls to a height of 1 meter. All right, so we're just going to plan on most of the time using our big equation that we just learned. So 1/2 mv squared plus mgy equals 1/2 mv squared plus mgy. What's the kinetic energy at the top of this, or the start of this motion, when it's being held at 3? Yeah. 0, because it's not moving. Okay, we're about to drop it. So our potential energy at the top is going to be mgy. Do we know the mass? Nope. They're going to end up canceling. I'm going to walk through with the m kept in there so that we can see how it cancels. Okay, we know that gravity is 9.8, and we know that our distance from the ground is 3. Good. Okay. What about kinetic energy at 1 meter? Are we going to have it or no? Yeah, because it's not going all the way to the ground. It's not coming to a stop. So we're going to have 1/2 m. We're going to be solving for v squared. Okay? Plus are we still going to have potential energy at the bottom, at the 1 meter mark?
Yes.
Yes, because it's still falling. So we're part kinetic energy, part potential energy. So m times 9.8 times 1. All right. So 9.8 times 3, I got 29.4. So that's going to be 29.4 m equals 1/2 mv squared plus 9.8 m. So what do we do now?
Subtract 9.8.
Exactly. We're going to combine like terms. So we're going to subtract the 9.8 m over to this side. Minus 9.8 m. Minus 9.8 m. So we get 19.6 m equals 1/2 mv squared. So now our m's cancel no problem, okay, because they're both multiplication and division terms. So these don't have a plus or minus sign in them anywhere. We're not adding or subtracting, so our m's cancel no problem. Okay? Then we're going to divide our 19.6, divide it by the 1/2, and then take the square root. So we'll divide by 1/2, divide by 1/2, and then once we get that answer, we'll take the square root. And I got my velocity to be 6.26. Yeah? Agreed? What's our units? All right, good. Excellent. Tell me why our kinetic energy wasn't 0 at the 1 meter mark. Still falling. Okay, if it had fallen all the way to the ground, then maybe we wouldn't have any. Okay, we'd have no potential there. All right. All right, this is assuming the height of the top hill of a roller coaster is 40 meters and the car starts from rest. Calculate the speed of the car at the bottom of the hill. Good guess. All right, we're going to go from the top to the bottom. Oops, not 28. 40 meters. Okay, we'll go back to our big equation here. 1/2 mv squared plus mgy equals 1/2 mv squared plus mgy. All right, so at the top here, at the beginning of our path, what types of energies do we have?
Potential.
Only potential. Okay, we don't have any kinetic energy because it's not moving. All right, so our kinetic is 0. We're going to have our mass times 9.8. And what's our y value? 40. Okay. Do we have any kinetic energy when we get to the bottom? Yes. Do we have any potential energy when we get to the bottom? No. It has no more potential to fall. 1/2 mv squared plus 0. So 392 m equals 1/2 mv squared. Our m's will cancel here. So 392 divided by 1/2. And we take the square root. And we get our velocity to equal... Yeah, good guess. I bet you probably did that in your head, didn't you?
I think I did it a couple years ago.
Oh, yeah. All. Okay, the initial part of our equation won't change at all because we're still starting at the top of the hill. So we're going to have 0 kinetic energy plus mgy for our potential. And then for our second half, we're going to end up somewhere down the path, but we're going to have both kinetic and potential energy because it's still moving. So we want to have 1/2 m What was half of our velocity from the last problem? 14. So 1/2 m 14 squared plus m times 9.8 times y. Okay, so this is still going to be the 392m. If you take 14 squared times 1/2, I got 98. And then for our last potential energy equation here, or term here, we need to have 9.8 m times y. All right, so now I've got 3 terms here. How do I get it down to just having 2? Subtract over the 98 so we can combine those like terms. Okay, so minus 98m. And that gives us 294m equals 9.8 my. We can cancel our m's. Divide 294 by 9.8. And we get our distance to be 30 meters. So it's not exactly at the halfway point that it has half its speed. Takes it a while to start picking up speed, and by the time it gets 30 meters down that track, it will have had half of its maximum speed. Okay. All right, last one. We're going to work this time with springs. Okay, this is our last problem for today. Let's stay focused, and we'll get through it. Okay. This one is dealing with our spring equation. Okay, so the dart has a mass of 0.1. It's pressed against the spring of a dart gun. It's compressed 6 centimeters. If it detaches from the spring when the spring reaches its normal length or when it reaches its static position, what speed does the dart acquire? We know our mass is all right. This all is saying is that at our initial position, we only have potential energy. At our final position, we only have kinetic energy. Okay? So if we have a mass of 0.1, we have our x, which is going to be what? You're both kind of right. What does the 6 centimeters need to be in? Meters. Negative 0.06. Okay. All right. So if we have all potential energy when this spring is compressed, yeah. Because if we have a spring that's just like normal, okay, and then we compress our spring, we're 6 centimeters back from where we started. Does that make sense? I'm really good at drawing springs. Okay. So if we have only potential energy when it's compressed, right? It's not moving, and it wants to reach its normal position again. So it's only potential energy. That means we're going to have 0 plus, what's the equation for our potential energy of a spring?
1/2 kx squared.
Good. 1/2 kx squared. Okay. Then at the second point, our spring will have reached its static position again, which means we have no potential energy in our spring. Okay, so we only have kinetic energy. Does that part make sense? Okay. So that means we're going to be at 1/2 mv squared for our kinetic energy equation. Our potential energy is 0. Okay. I want to make sure that we feel comfortable with where these zeros came from and how it lines up. Is that a yes or a no?
Yes.
Okay, so now we can start plugging in numbers here. All right. What is our K value here? 250. 250, and our x value is negative 0.06 squared. 1/2. What is our mass? Our mass is given to us. It's 0.1. We're trying to solve for v. All right, so on the left side of our equation, what do we get? The whole left side equals point. No, because this 0.06 should be squared, okay? And then on the other side, 0.5 times 0.1, 0.05 equals 0.05 times v squared. So our velocity we ended up getting as 3. Okay, so here's your homework assignment. You're doing 35, 37, 39 through 43. On number 42, you only have to do part A. You do not have to do part B.